Not yet. No.
Okay, now yes.
All right, so hello everyone. We are from the module Emerging Fields in Architecture at TU Vienna, and it's a module in the architectural master's degree which focuses on innovative topics in architecture itself, and has also a lot of guest lecturers who present from their work and what they do. And we will learn today about Vittorio Netti's work. He's a PhD candidate in aerospace engineering and a Master of Science in Space Architecture, and also researcher at SICSA, which stands for the Sasakawa International Center for Space Architecture at the University of Houston. He filled the commander role at NDRS and participated in different analog missions. He has published several scientific articles and books on the topics of space architecture, system engineering, and aerospace engineering. So as a space architect, he works as a consultant for different firms, research entities, and aerospace companies such as Surge Plus, Hessel, Boeing, Robose, and Sierra Space, and space agencies like NASA and ESA. In his free time, Vittorio loves to fly his drone and is an avid diver. And I guess there's also one correction. Please.
Thank you for the introduction, Alexander. Can you hear me clearly?
I can hear you clearly. Thank you.
Okay. Well, let's dive in at this point. So as Alexander correctly said, I work at like this presentation is related to my work at Sasakawa International Center of Space Architecture here at the University of Houston, where I am right now, and not in space. But so like my work here is focused mostly on the fields of using XR, that stands for extended reality, for as a new tool for design and testing of space habitats. So this is my personal research that I brought here at SICSA. It's quite like it's like a couple, like almost 3 years that is going on, and I created the XR laboratory here at SICSA. That I will explain what it is, what we do in a minute. So let's start from one, because I just said XR and here it's written VR, and I know this can cause some confusion, and I'm pretty sure that many of you are already accustomed with those concepts, but I will make some initial definitions just to be sure that we are on the same line. So let's talk about extended reality. That is the term for which it stands, XR. So XR, it's like a family name for different technologies. Mainly, we include the three that you see here that are virtual reality, augmented reality, and mixed reality. So VR, AR, and MR. As probably many of you already know, like VR, it's pretty common right now in the last years, thanks to the democratization of the hardware, because now the hardware costs really went down thanks to players like Meta, that they started selling their virtual reality headset for less than $300. The technology advanced really fast in the last few years, exactly also for this specific reason, because when the cost is dropped down and so it's get more diffused, so there are more people, more stakeholders interested into advancing this technology. So more funding get pumped in, and more companies they working on it, and that's why we have seen the exponential advancement of this technology nowadays. Also, let's work with the AR. AR as a technology, augmented reality, had a big boom years ago, but after it was already mentioned, after the failure of the Google Glass project, but still they brought a lot of AR innovation in our smartphones that are our main AR device right now, that is in our pocket all the time. And the difference of virtual reality, AR, is a system that overlay digital information over the real world. So it's use our vision, or in the case of the smartphone camera, as an eye on the real world, on which after we overlay a layer of information on it. And the difference of virtual reality, that's literally create a digital, inexistent world in front of our eyes. After this, the mixed reality. Mixed reality, it's a bit, as like the name say, in the middle between the two. So we still see the real world, but the digital world is very much intertwined with that real layer. So basically the idea is the digital objects, they should blend in kind of with the real view. And so that's make another level of immersivity compared to what we have right now. This is a mixed reality. It's actually a term that has been invented by Microsoft a few years ago. And now it's more and more relevant, because the technology is enabling finally this technology to become real. So now that we agreed on what XR means, let's do a little excursion about on the different topics. So they have many applications. Because this year I listed the main fields for which these technologies are used, and it's architecture in industry, and for industry I mean mostly like manufacturing and assembly, heavy industry, military application, of course, medical, and entertainment. Here there are three of the main focuses for which this technology is used. Is design, review, and training. We started with the third. The training has been immediately the initial focus of this technology, because we didn't have still the interaction capabilities to work on the other two. But now the technology advanced, it's very much developed also for all these other two different purposes of this technology. So how it works when from the other side, from our side, the coder side, the designer side. So, well, the first step is common with every other things that we do. That is the design phase, in which we use CAD softwares that can be meshed, they can be solid, like Blender, SolidWorks, Maya, Rhino, whatever, to create our digital models. And those can be the same models that we use in a certain way for our other purposes, like design evaluation, manufacturing. But after there is another step, we migrate to another software that is the VR engine. There are basically two engines on there. They are both free to use. It's a Real Engine and Unity. They are also pretty much similar, but different at the same time. In which we create our VR environments, and we create our interaction. So we can't model on these softwares, but we can integrate our model inside the environment and define the interaction that we will be able to have with the objects in virtual reality. This family of software is the same that are used to create, for example, computer games. The third step is an exact integration between the two things, the environment and the assets, and of course, the testing that validates what we did. So this was just a bit of background in order, so when I talk about something, we kind of are on the same page. let's talk about the role of extended reality in space. So as like right now, like virtual reality and extended reality in general, as like a lot of consumer applications, as we've seen before. I don't know, many of you have already tried virtual reality, for example. Most of my students here at SICSA, they already have some kind of experience in virtual reality, fit for their work or with friends that they own their own headsets or things like that. But actually, it's not a new technology. As you can see, NASA created the View. That's the first this headset that you see on the left in 1981. It was being for the first try to be integrated with astronaut training in 1985. It was dismissed in 1990s when the technology was deemed too early stage for that kind of application. On the right, you see a more modern training application that is basically, well, in microgravity, we don't feel the weight of things. So the idea that they at NASA that they had, we can just stick a laptop on your face and it will be a good headset. So how it works, that's how it's possible for one reason. I didn't put like the technical slides on how virtual reality works and extended reality, but basically what we are doing is that we are generating two different images that are shown to your eyes, and those images, they are stereoscopic images, so they have a slightly different camera, like in the way that it's like your eyes are two cameras, and they're of course placed at a small distance within each other. So the image that they're looking at, considering that they're kind of the same field of view, is slightly different. That's because, of course, the position of the camera is different. So what the computer is doing when it's creating the illusion of virtual reality is basically reproducing the stereoscopic system of our eyes, and so proposing to our single eyes two different generated images of a three-dimensional space. Since like those images, they come from two specific point of view, when they overlap through our eyes, they give us the illusion of depth. That is exactly the reason why when we look through a virtual reality asset, we can perceive the depth. Anyway, so what's like a computer does is and this is also the problem for which like this virtual reality application are usually like less real in terms of graphic quality of, for example, video games or movies. It's usually because it's basically the computer has to run two different applications, each one from a slightly different camera. So it's basically running two software at the same time just to have the images, different images presented to your eyes. What is like a extended reality is used in space? Well, first of all, because of course it's create a situation of augmented immersivity inside the whatever simulation it is. Just because, of course, what we can simulate on Earth, like for example in the neutral buoyancy pools or inside the mockups, they will lack so many elements. For how like high fidelity can be a mockup, you will never have like things flying around. For example, you will never be able to see the Earth spinning behind you without the correct parallax and certain other things. You will never be really able to experience the disorientation that floating and just like flying in microgravity will give you. So augmented reality, it's a cheap way to go to space and to test many things. You can have simulated tasks and simulate the consequences of the tasks. That is something that you can't do in normal analog simulations. Like, for example, if I do something, I break something, and or like I make a mistake, and this creates us an hazard. And so, for example, something fell apart or explode or take fire or anything of this other situation can't be reproduced for real in real life. Can instead be reproduced easily in virtual reality. So in space, it's usually now more and more the XR simulation are based on the mixed reality. So we use mockups on which we overlay a digital layer that's help us simulate the situation and the tasks. It's definitely so based on the physical interaction, because while instead when we use virtual reality for entertainment, for example, interaction with physical object is less important, while instead for astronaut training, for example, we want the astronaut to develop like a physical memory of what they're doing on their task. So know what to touch, how to touch it. And so for these purposes, it's important that we should have a physical interaction with object, even when we are in virtual reality. It's cheaper and faster than mockups, because if I have to build like we will see that an high fidelity mockup of the space station, it will take months or years sometimes, and it will cost millions of dollars. While an application, of course, as you can imagine, it's way faster and cheaper to build, and it's more iterative, but we'll talk about it later. It can reproduce the disorientation, because what the motion sickness that the astronauts experience in microgravity, for example, is due to the fact that there is an impairment between the inner ear, that is what regulates our sense of equilibrium and balance in our brain, with our senses. It's the same thing that happened with car sickness or boat sickness, seasickness. What happens is that our inner ear perceives a certain balance, okay, of the space around us, but our senses, like our vision or our hearing, is in contradiction with that balancing that an inner ear feel. So our body in that situation is convinced that we are sick, there is something wrong with us, and it activates some countermeasure, like let us throw up, because it could be something that we ate, and so we are intoxicated, and that is the reason why we throw up when we experience seasickness, for example. Virtual reality can easily reproduce this sensation of nausea and disorientation, exactly because perhaps we are looking at a simulation, but then our inner ear is still perceiving that we are on Earth, and we have a certain horizon, a certain orientation of that horizon. So this like impairment give us the sickness, and so augment the level of immersivity of using these kind of tools. And as you can see from this image, a very nice feature of using extended reality in space, and we can easily use the same simulation in space and on Earth. We just have to bring the headset up there, and we can experience literally the same thing. That is something that's often is not possible. So what are the applications? Before we look at the general application of virtual reality and extended reality in space, here we are looking at their application. In the general industry, and now we said that we are looking at the applications of this technology on just for the space industry. Mainly, we have like 5 fields: there are testing, training, robotic control, enhancement, and design. What this means? Testing is like we can easily test something that we designed, and we don't know if it will really work, and so we can in a cheap way we can make a VR simulation and having astronauts and other stakeholder testing it in order to be able to say, oh, that's a good idea or not. when the things it's already been approved, and so we have to train astronauts to use it, to use our design. So that's when we need training. So at this point, there are specific procedures that need to be tested, and so it's about training the people that will use it in space in order to be sure that they will not have problems when they will get to space and they have to use it. This is the most common application for virtual reality. There is also robotic control, and what I mean is that, for example, if you consider things like robotic assets like the Canadarm on the space station, we are controlling an enormous robotic arm in space, in a three-dimensional space, okay? What is the problem? That usually, because it's remotely controlled, you don't perceive the depth, okay? So what you have is you have just some cameras, so it's a bidimensional image on a screen. And it's very difficult to control an object, especially a so dangerous to control object, or in a three-dimensional space using a bidimensional view. For this reason, in fact, most of the astronauts, when they control the Canadarm, aside from the fact that they tested and retested again and again those same procedures many times, and they end controlling the Canadarm through the numerical position of the arm in space. So what they were doing, especially on the space shuttle, where there was also the Canadarm, just reading the infinite prints of positional data of the inertial motion units that they were on board of the robotic arm. It's basically like reading the path on a car, just looking at the progress update of their GPS coordinates in numbers. But for the astronaut, that was more meaningful for them to control the Canadarm than actually looking at the images on the screen. So that was why, because exactly through the screen they couldn't perceive the depth. And this is a fundamental tool to not crash the robotic arm inside the satellites or inside the space station. With virtual reality and mixed reality instead, we can actually have the perception of depth. So we can control a robotic arm remotely, like it's our whole arm. This is exactly the purpose of the stereoscopic vision. Like when you take your arm and you reach for something on a table, you don't need to think about what's the distance between your arm and the object. You like intuitively know that distance, and you go and grab that object. Okay, that's because you have the stereoscopic vision, and you have in your brain inbuilt this concept of depth, for which you are able immediately to extend your arm of the right distance in order to grab that object. These things can also happen with robotics if we have the stereoscopic vision of the camera on board of the robot arm. Enhancement is what you see on the right. So we are talking about enhancement of human capability, enhancement of vision, enhancement of hearing. I mean, so for example, in this way, we have enhancement of information. So a human will not be able to know immediately all this data about the spacesuit that is wearing, like the oxygen level, battery level, CO2 scrub level, and things like that. He will need to go and look at a device in order to get the information. And so in this way, he will be distracted from what he's doing. And this is also makes sense in terms, for example, navigation. Imagine that an astronaut is driving a rover on the moon, and as, for example, Google Maps right now does, you can have the possibility to have your path that is literally printed inside your helmet. So you can actually navigate without the need to look at the map. This is called enhancement. So we are enhancing human capabilities, like giving us a superpower in a certain way. Like, for example, the one of knowing the oxygen level of the spacesuits without the need to look at it. The last one, that is in yellow because it's the one that I work on, is instead using XR for design phase. So all these phases that I'm talking about, they come later when I already designed our things. But what if instead we use virtual reality in the design phase? This is a more common thing. It's like a bit of a revolution that it's happening in the same way as the computer-aided design revolution happened years ago. And when it happened, everyone was saying, "Oh, but the computer will never be the first way in which we design something. It will be the one in which we refine our design, but we will never start working in 3D." And this is said mostly what we do. There are softwares, especially mesh software, but also is the modeling software in which basically you start to design from the 3D. It's actually the most intuitive way to design something because we reason in 3 dimensions. So like it's kind of unnatural for us. We've been taught since when we were a child to imagine things in 2 dimensions in order after to design them for 3 dimensions. That is not the most efficient way to do something, because what we do is we convert our idea in B-dimension to after retransform it in a 3-dimensional object later when it's manufactured. Doesn't make a lot of sense, while it's making more sense to work already in 3 dimensions. Now we have the possibility to work in 3 dimensions inside the space within the object. It's a bit like sculpting in real life. And this, I think, it's really changed a perspective for which when I started understanding how to do it, so like designing, for example, really already in virtual reality, it's a so much powerful and straightforward and efficient way to design anything. So let's talk about what we do at SICSA. That is what I do at SICSA. That is the what I call it the XR design framework. So the goal of the framework was, there were like 4 goals. It was create an extended reality infrastructure for iterative, this is very important, design testing of space hardware. This is his main statement. Define a standard evaluation system to implement the design assumption derived from extended reality tests. What that means? Well, engineers loves evaluation systems. Okay, so like, okay, we did that, we designed that, but how we say that is the best option out there? So what you usually do in the space sector is create these enormous tables in which the different results are inputted in. It's an evaluation matrix, how they are called, and we have basically a grade for each of the design option, and which you say, oh, this option is better than the other. So we knew that if we wanted to make this system widespread across the space industry, we needed to create an evaluation system that allow us to understand like how those design testing in virtual reality will transform in design derived criteria that we can implement inside our design. This is also for another reason, because when I started this project, the first things that I did, I knew that many people that they were like working already in virtual reality for, in the space industry, both at NASA, in other companies like Sierra Space and Blue Origin. So the first things that I did, I started talking with them. And trying to understand how they were using these tools, how they were trying to implement those tools inside their processes. What I understood at the time is that they didn't know how to use virtual reality. It's basically the idea is that they understood the potential that virtual reality could have inside their design processes. So they started hiring people from the gaming industry that were accustomed to this idea of designing virtual reality and using virtual reality, but they didn't know really what to let them do and how to implement this technology inside the process. So it was always being like a side technology. That's oh, let's see how let's look how it's look like. Oh, it's look cool. That's nice. But after there was no derivation of this virtual reality design thinking inside their current design processes. So that's why we needed a standard evaluation system. The third point is to define a multi-mission procedure testing framework based on highly immersive XR technology. What that means? That means that we want to create a framework. The technology advances, I say, very fast. In few years, it's really changing and is expected to grow faster and faster. So we don't want to create a static framework that will be in few years or in few months already outclassed by the technology itself. So we wanted to create a framework that would adapt to new technologies and new hardware and new assets in a very flexible way and the resilient way. The fourth point was to create a framework that will grow the new XR capabilities in the space sector. So the framework should not just work for its intended purpose, but it should also give the opportunity, possibility to create new purposes and to create new way to use that technology for different applications still in the space sector. These were the four cardinals, cardinal points in which we start designing the XR framework. What it is? So the XR framework, it's both a physical and a digital space, but also it's a validation standard. So there are these three layers. There is a physical room. It's like we call it the cage, where we do the testing, and everything that is happening inside the room is tracked. There is a virtual space. There is the software on which we bind the digital space on the virtual on the real space, and there is a standard manual that tells us how to use the space and how to perform the evaluation metrics and understand which are the right design criteria for this testing. So this is how it works, how it is right now. It's a multi-gravity testing environment. So as you can see, there is this crane inside the room that's allow us to conduct microgravity simulations. We are still not at the point in which we can test multi-gravity operations. Like we can test now just microgravity or kinda ground simulation, because we don't have an active crane system like the Argos at NASA. An active crane system, it's a system that uses a computer to calculate how much force the person is putting on the harness, and so it will react, and so you will basically, you can simulate walking on the moon or walking on Mars, just changing the gravity level on the controller. Why the green screen? You will understand it later. But this is how it works on paper. So this is the NASA design loop based on the System Engineering Handbook Revision 2. That is the last one. So we have these four groups, that is the stakeholder expectations about the project, that they get into the requirement definition, that they get into a logical decomposition of the project, that they get finally to the design solution definition, that is the real design loop. So where the magic happens. After if the things worked, accordingly to the requirements, the object goes into production. Instead, it will get feedback into this loop until we don't get a solution. So as you can see, the design solution definition is the one that's it's interesting for us. It's already a sub loop that has its own problems. Okay, so how it works? There is the concept. We start from the right, so develop design. So we develop a design or many designs. We compare them with the different design option, and we compare them with the different requirements that has been defined before. There are the CONOPs, the concept of operations. So we run that design through the CONOPs, so through the different steps in which that space of hardware is designed to work within. And so we evaluate, okay, so how well that design performed inside that concept of operation. If the object meets all the success criteria, it goes out of the design loop and it goes into production. Instead, it will get reiterated until we don't get a solution. What's the problem? The problems with this current design loop. So often the iteration testing is iterative testing that is limited by resources. So if every time that we test, evaluate part a design, we have to build a mockup on which we can test that design. The mockup takes months and take a lot of money to be built and tested. So what happens at NASA in many other contexts, that at a certain point they finish the money for the mockups, and so they say, okay, that's fine. That's basically it's the end of the iterations because we can't continue iterating it. So we'll be fine with what we have, or the rest of the implementation will happen without the mockup evaluation test. The evaluation is subjective, so usually the evaluation part is made based on it's based on some questionnaires and surveys that the people that tested will answer to, that are usually qualitative. So how well you felt that you performed this task and things like that. So actually all this evaluation part is subject to the bias of the people that test the design. Also, there is no evidence that connects this evaluation with design-derived assumption. This is another big problem. So those people, they say, oh, okay, this design was good, this design was bad. But after there is no measurable way that will convert those surveys with some indication of what to change the design. So it's basically the designer itself that say, oh, that's people answered it like that, so we should change that aspect in this way. But I think that instead there is a more scientific way to make this correlation between exactly this evaluation and what we need to change to make the design better. So it's what they are called the design-derived assumption. So since it's very complex, all these loops, also the low iterability, it's also connected to that because the design loop is so strenuous, it's full of the steps and information that sometimes, if not the money, we finish the time that is allocated for the design. And so we have to go with that design because we don't have time to iterate it anymore. So it's not forcibly the best design that there is. Also, often the design, the mock-up testing, the one that you see at NASA that is done inside the Building 9 is done after the design phase. So they build just some small low fidelity mock-up and that's it in the design phase. But when you go to the phase in which you do the real mock-up test with high fidelity mock-ups, the object is already out of the design phase. There are a few things that we can tweak, but the design is fixed there. So this is another problem of this current solution. So to answer all this problem, we introduce the XR framework testing. That we don't want to erase the current design loop, but what we do, we run in parallel, and it's a way faster and more iterative. So we can run many more loops in the same time, in which through this procedure, we run just one design loop. Because in what we do in the virtual reality is we use extremely low fidelity mockups. This is the reason for the physical space. We still build mockups, like the spacesuit that you've seen before, or the drill, the PGT drill that you've seen before. Those are low fidelity mockups. That means that are mockups that they look kind of like the final object, but they are cheap and very fast to build. What we do is that we bind those low fidelity mockups with the high fidelity digital models. So you will be able to touch the low fidelity mockups, but in your virtual reality headset, you will see the very high fidelity one. So we mix the best of both worlds. So the physical interaction capability, but also the idea of working inside high fidelity mockups. So this whole loops, how it works for us. So we create to solve the problem of the subjects of the evaluation and subjectivity of the evaluation, and the non-correspondence between the outcome of the design, of the evaluation phase and the derived design assumption. This is the inner loop that we created inside our XR framework. So we break down the human system integration performance evaluation in two branches: the human performance and the hardware performance. What that means? That means if for example, if I'm trying to evaluate how good I perform a task inside a space station model, okay, from one side, I evaluate how good me as a test subject, I performed the task, okay? And on the other side, I evaluate how good was designed the hardware to allow me to perform the task in the correct way. So we still rely on the two most accepted questionnaire-based evaluation by NASA, the NASA TLX, that is a task load index that measures the human performance, and then MSAS, the modifying system usability scale, that is still a questionnaire that is designed for hardware performance evaluation. But on top of that, we add a biofeedback level. That's what this means, that the people that they test designs during the design phase with our system, they wear a suite of sensors that is meant to validate the data that's come from the questionnaire. So for example, if in my questionnaire, I said, oh, I was not stressed at all performing the task, or this task was very easy to do. But after I see through the biosensors that instead the level of transpiration was very high, the level of the heartbeat was very high, the respiration was very fast, this is where I identify a bias. And so I can eliminate the outlier. And so I can say, oh, this actually questionnaire is not valid for our performance evaluation. All this data, they get weighted inside, they get a weighted score. So each value, I will not show you that the data for now, like the different aspects on which we evaluate the data, for two reasons. One is because it's a very long thing. A second one is still partially proprietary of one of the project partners, is Boeing. But this weighted score, they get into an evaluation matrix that give you exact derived design requirements for the next iteration of the design. That means that, for example, that questionnaire that I create, that evaluation matrix that I create for the specific piece of hardware evaluation, it will tell me the position of this console is not right. You have to move it. And looking at the MSAS evaluation, I can also tell you where I should move it. I should move it on the left or the right or up or down. Like, this is the level of detail in evaluation that we actually want. So as you've seen before, here we have the two ways in which we can use it as surface testing or microgravity testing using the crane. We will work on an active version of the crane, so we can simulate multiple level of gravities within the crane. And let's see if it works. There is a video after. So now you will understand why the green screen. So a big problem about the virtual reality simulations, it's usually is that you can see from the outside. So if I am the evaluator or the designer, the only things that I have as data are the questionnaires and the camera field of view of the person that is performing the task. So I can see exactly what is looking at the person who is performing the task. What I can see is that person from an outside point of view performing the task, because that person is in a virtual space, it's not in a real space. And this is a problem. It's a problem because all the evaluation that are done through testing right now for space application, for example, the ones that are made at the NBL, the Neutral Buoyancy Lab, here at NASA JC, or in the mock-up testing, they are done through external cameras that look at the scene, and so I can see from an external point of view if that person is performing the task correctly. To solve this problem, we create the green screen part, and we coded a piece of software that allow us to see in real time the person performing the task inside his own virtual reality environment. So as you can see here, I will have on my screen, while I look at the person performing the task, both things. I will have her is like a first field of view on the right, and on the left, I can have himself placed inside the environment is in exactly the position in which you have, possibly for multiple point of views. That's in every point of view which I place a camera. So this allows us to dive literally into the virtual reality simulation together with the person that is performing evaluation. So this is a game-changing feature of our system. Another feature is we use full body tracking suites underneath the spacesuit, for example, that give a perfect understanding and tracking of the people movement inside the EDVS. EDVS is the name of the infrastructure that stands for Immersive Design and Validation Space. Here you see just a small demonstration of just the gloves, but we wear full tracking body suits. So you can understand perfectly and record perfectly the movement, and you can, after overlap, for example, the different movements that are performed by different people performing the same task. So how it's going? In 2021, it was just a sketch. 2022, we have built the cage. That is the meta structure that you see inside. The cage also hosts all the sensors and the cameras that allow us to track all the movements inside the space. And now it's completed. As you see, the current development 2023 with the crane and the green screens and the mock-ups finished. Here there is our control room on the left and some of our headset tracker So what are the trackers used for? The trackers are, as they're called, trackers. So what they're used for is to track the low fidelity mockups in the digital space. So as you've seen before in the video that I shown you, the person was carrying a box, and the box was just like a plastic box. This has been bought at Home Depot for $14. But the person in the VR headset would see a high fidelity lunar sample box. And this is possible through the tracker. So the tracker, it's bind that physical object in the digital space. And so we can bind that digital high fidelity mockup to the the high fidelity model with the low fidelity mockup. Here you can see on the right the VR tracker integrated on the PGT drill. So this is the entire drill. It's 3D printer. It's 3D printed, and so basically in this way, using that tracker, when I can touch the drill, but I will see in my field of view the high fidelity PGT drills with also all the regulation that the drill itself has. So here there are some photos of the both modes in surface testing and microgravity testing. Next step of these projects are, so we are preparing a test campaign with Boeing. That is the main funding source for this project in an habitat, minimal habitat that we designed for them. So like a 14 cubic meter space, so very, very small, which 4 astronauts need to live for 2 weeks for a lunar mission. So here there is also on the bottom, you see basically the sequence of the testing for each of the user. Is a training part, and after the test part, they will perform 4 different tasks, and after the brief. And we will repeat the same experiment for many users, possibly to cover different heights, different weights, different genders, different level of experience with virtual reality, because of course a person that has been accustomed to working and playing in a virtual reality environment will perform way better than someone that never touched a virtual reality headset in its own life. But this will not stop there, because that specific EDVS, as I call it, like our framework infrastructure, can be used for space hardware design, as I was saying before. So the idea of designing really in the 3D space. And so imagine that, for example, you are designing a space module, so you can take consoles and move them across and move different volumes in real time and see how they look like, how they test like, how they perform. Mission procedure testing, that is what we are doing right now, and after also the idea to performing telerobotic operation in a virtual 3-dimensional immersive space. This is another capability that our system has. So we have 3 partners. We have 2 partners. We are 3 partners. There is the SICSA plus Boeing. And recently we partnered with Buendea. Buendea is a company, it's a virtual reality development company that make the XOS. The XOS is the virtual reality engine of NASA. So we now work on the same version of the engine that NASA use with their same simulation capabilities. Now I show you something of the things that we work on that are developed by Buendea for NASA at NAOCL, that is NASA Advanced Operation Concept Lab. Here, everything that you can see, it's already virtuality graphic. Okay, so this is what we see in virtual reality. So here you can see teleoperations, This is our PGT drills. This is a martial operation. This is cave exploration. This is inside habitat. We use in a project that we developed at Hassel. This is multi-user. That's what we do in our room, that we do multi-user development. We can simulate environmental conditions, like lunar dust, for example. We can simulate driving rovers on the moon, on Mars. Now, when they are recently implemented very high fidelity lunar simulations. That is what you can see right now in preparation for the Artemis missions. And you have real shadows and Earth and sun moving across the sky to have high fidelity levels of lighting, for example. Yeah, and this is everything that we can do right now. This is all our capabilities, simulation capabilities with the Wien / NASA software. Also, you can download, like, there is a public version of XOS that you can download and use on your computer. You will need a very powerful computer and include some of the capabilities that are shown right now. So I really suggest you, if you're interested in the topic, to go ahead and try it by yourself. On top of that, a last announcement that I wanted to do is that, so together with the AEA, that Architectural Association, that is probably the biggest and most ancient and most famous architectural association in the world, the UK one, we created Moonshot. There is a visiting school by AEA that will take place. Already the unit 1, that is anthropological one, already took place in London. The phase 2 will take place now in Houston, and this is exactly what we will do. So the idea is to mix together architectural design and virtual reality and parametric design, artificial intelligence, to imagine a society living on the moon in 100 years from now. So the idea is that we will code AI that will design our moon city through Unreal, and we will simulate inside our infrastructure. And will take place, like, there will be tutors from Wien, from NASA, and from people that work in Star Wars, and all this immersive simulation for the space industry. Icon 3D, we will go to visit all these places. Here, it's like some of the digital simulation that we are preparing for the workshop based on the Wien software. Will take place between 26th of March and the 5th of February 2024. You can contact me or go to these addresses to get more information about the upcoming workshop. It also will be a yearly thing, so the plan is to do it every year. The Houston part will take place here at the Sasakawa International Center for Space Architecture. It's also a very good opportunity to visit and work here for a week. And that was it. So thank you for listening, and I'm open to questions.
Yeah, thank you very much for the interesting talk. So as usual, please put your questions that you have in the chat. And since there's already one, which is by me, I will start by asking that, and then we'll see what else comes up in the meantime. So I'm wondering if you're aware of the cave from HLRS Stuttgart, which is also like a multi-user virtual reality environment, which they use for maybe mostly building information modeling and site analysis and stuff like this. And it's basically a cube which has screens on all sides, which generate 3D images for the users. They are also tracked with infrared cameras. So it's kind of a similar setup to what I believe you have going on. And they use that to have there sometimes even 10 to 15 people walking in and working together. And I'm wondering if an approach like this is also something that you're kind of considering because there's already examples which are working, or if you're more focused on the individual head-mounted displays and having multiple users only via synchronizing their, virtual images.
So no, I know that kind of systems. So there are, of course, some advantages and some problems. The problem is that the level of immersivity is lower. You can't. It's more difficult to interact with physical objects. So they're more interesting for certain to reproduce certain conditions. And I think that they have more value in the framework of communications with the public than for internal testing, because especially now that the headsets are getting so much smaller and lighter and the field of view is getting larger, I think that also there are less advantages in using those kind of system over virtual reality or mixed reality in general. And also there are certain things like it's difficult to test, but that doesn't mean that it's not useful. I know people that, for example, they use it in construction. So they have like a warehouse where they can simulate different layouts of apartments and houses. And so you can change kinda in real-ish time the interior layout, and you can work through it. So I think that's for conceptual phase, they're very good. Also the problem in a certain way, I think that they require a big infrastructure. While potentially our system can be used with just one headset. Of course, like having the cage, how we call it, it's enhanced the level of like the features and the options, but potentially we just need a computer headset. Actually, sometimes we don't even need the computer, because now many headsets they are standalone, so they don't need if we just have to perform the task, I will just need the headset itself. That it's a very important point, especially now that we collaborate a lot between the academia and the private industry and the national agencies like NASA. Often those things are performed in different places at the same time. So with virtual reality headset, we also have the advantage of the telepresence. So different people can collaborate on the same project from different places in the world and being in the same room.
I see, thank you. So there's another question from Mihaly. If you want, I can also read it out.
Yeah, sure. So what I was wondering about is that what are the hardware requirements for having so detailed rendering and having so detailed virtual simulations with the shadows and the weather changing, and to really make it immersive and as real as possible for the people?
The requirements are kind of crazy. Like they're very high. So for example, here we use a couple of very powerful high-end Alienware computers, and they barely can run the NASA version of XOS. The public release one that you can download from the Unreal Store, or from their website, it's more usable. It has way less features, but it's definitely more usable. You just need one of those like gaming laptops or computers, and it works fine. Like if it can run like a virtual reality game, probably can also run that. But yeah, you work on completely different scales. I learned myself because I was thinking we were good with the requirements, but actually I found that we are really on the edge on that point of view.
Thank you.
There's another question by AT. Adrian, if you want, I can read it out.
Yeah,
Oh,
please.
sorry, I can read it out. Thank you so much for the presentation so far. I was just curious if there are astronauts with real space experience that have tried the headset and the XR environments, and what their feedback was. How does it compare? How does it differ, if there is such feedback? Thank you.
Yeah, this is an interesting question. So most of the astronauts, of course, the astronauts say, of course, like the being in space is different. Okay. But this is definitely what they say is that this is the most helpful way to simulate that kind of conditions for them. So at the training level, having mixed reality experience in which they can see the things and touch the things and manipulate them is the most immersive dry run possible that they can do. Of course, like depending from the operations, because now that we have technology that like the Argos system that I was talking about before, this is active multi-gravity system that in conjunction, if worked in conjunction with the spacesuit mock-up, if worked in conjunction with the headset, with the simulation and everything, so they give you a pretty good range of like of similarities with what they're gonna do. But it's completely different from reality, the reality of being space, at least what they say.
Thanks.
So are there any more questions?
I would have one other question I'd be interested in, because I'm an architect, practicing architect, and I've tried to integrate augmented reality in my workflow with clients as well. And I've tried the headsets myself, some very high-end ones in London as well, in architectural offices. I've always had this issue with the nausea, especially in the complete virtual reality, with the complete virtual reality headsets. And the mixed reality was always had some confused reactions from people who aren't familiar with the technology. I was just curious if you are putting an effort into sort of making it more accessible to working, to model, and to reach the environment faster, as they do in the film productions with the new sets with a turnaround green screen? Or is it still it seems like a very laborious process of modeling and documenting and constructing everything, and I was curious if it is in fact such a laborious process as it seems, or if it's actually it's way more friendly than this and way more approachable.
No, it's definitely got easier, and there are some tools I have to say that are so easy. like Twinmotion, for example, that's like meant exactly for architectural simulation. It's basically a software inside Unreal. It's definitely, it's not easy. It's getting easier, but of course, like the idea is that it's still a kind of like it's like a branch of coding. It's like mostly visual coding, what you do in virtuality and augmented reality applications, but still it requires a high level of understanding, in the same way in which architects, they spend their time on BIM softwares and everything else. It's just a different expertise. Like a different expertise is designing for virtual reality and augmented reality. Like NASA has an entire office that is called here at the JC, that's called the Hive, in which they design augmented reality interfaces for the astronauts. And the point, I think that designing for augmented reality, and so designing for someone that needs to use that augmented reality, they don't need to know anything about what you did, what you code. They just need to use it. They are the end user of your augmented reality interface, require extreme specific skills and extreme specific sector knowledge. There are entire like degrees in user interfaces and user experience for XR. Okay, there is one famous in New York, for example, and things like that, for which it's not an easy job, definitely, to design for virtual reality, augmented reality. But there are definitely ways to make them easy for the user. It's just like it's really just like a matter of knowing what to design, how to use it, and that's what I'm saying. I think that there is the problem sometimes, because I too have an education in architecture first. After I studied aerospace engineering and space architecture, but architects, it's their I think it's their advantage, but also their curse, that they think that they can do everything. And I don't think this is the case many times. They are able to understand everything. And this is, in fact, it's the reason why architects are great project managers. And often at NASA, there are like people that start as space architect and like a project manager. Myself, I did that many times. But to do certain things like design interfaces and design user experience for this application, for the final user, the client, you probably need a specific UX XR designer. That's my suggestion, like how to approach the topic, at least as like as someone that can check and can help you your work of integrating. Instead, it will be always very difficult to create something that it's usable for, as you say, for someone that has no experience with that kind of technologies. And of course, there is also another layer that is the technological layer. There are headsets like the Varios that are produced in Denmark, I think. The Varios, the most advanced headset that they are out there on the market. They cost $10,000, and they have a perfect mixed reality integration, for which it's almost undistinguishable, the digital layer for the real layer. And of course, they require a lot of knowledge on how to integrate those high-end models, and they require also high-end hardware, but are definitely a solution also for this problem.
And do you guys plan to take some extremely high definition scans of the moon and sort of integrate them in the XR space or the VR space? Because I think Unreal 5 has now this highly detailed models of the real world that you can use as assets, and it seems like something that'd be interesting to do, to sort of map everything out in the highest possible detail and interact with the environments on this level. Personally, I found Unreal 5 extremely complicated to the point of being not useful really for the workflow of architecture, and I migrated to other engines. But I do understand that it's very attractive, and it has this possibility to present things with high fidelity. Anyways, thank you so much for
You're welcome. For the Moon thing, it's actually there are, for example, the NASA software that you use is connected to a cloud database, and this is more and more common in not this application. Also, like to create, as you were saying, like word tiles with high definition. It's based on the fact that you don't have the data stored. The data are pulled out of a database through a query request from the cloud. So this is the only way in which you can are able to get that level of precision and that level of definition, but also the fidelity of the environment with the real thing. But yeah.
Thank you. Are there any more questions? I also looked at YouTube and there also seem to be no questions at the moment. So let's see if there's some more. All right. If there are no further questions, then I once again say thank you very much. And it was a great talk. Thank you. And also in the name of Sandra Höblig-Meusburger, once again. And yeah, I will then close today's Zoom meeting on her behalf. And yeah, wish you all a pleasant evening.
Thank you very much for the opportunity to talk with you today. I hope you enjoyed the presentation, and don't hesitate to contact me if you want more information on to ask other questions.
Many thanks.
Thank you. Good evening.
Thank you. Bye-bye. Thank you. Bye.